What's up with those bright, tiny lights in the night sky? How did they get there? What do they do? Well, fear not. All those questions and more will be answered in this epic edutainment video. Outer space is filled with nothing. Well, almost nothing. It's filled with little particles of hydrogen and helium created from the Big Bang. They make up about 99% of all the matter in the universe. Eventually, these elements get pulled together by each other's gravity until they form interstellar clouds, 1,000 times more massive than our own sun. These stellar nurseries propagate throughout our universe, making beautiful shapes across the heavens. But our story doesn't end there just yet. This is just the first stage of 7 in a star's birth. After around 2 million years, it can collapse into multiple different fragments, each able to become a star of their own. Eventually, a fragment becomes so dense that radiation cannot escape it, and the fragment begins to heat up. In the next stage, the fragment's gravity continues to shrink the fragment as the cloud gets hotter and hotter. It's still larger than our solar system at this stage, but that won't last long. In stage 3, the fragment gets dense enough for the center to become fully opaque. The middle core is now known as a protostar. Protostars still cannot reach fusion, and the light it emits comes entirely from the decreasing gravitational potential energy. After about 100,000 years, the protostar gets hot and dense enough to be plotted on the HR diagram. But what is the HR diagram? The HR diagram plots the temperature against the brightness of a star. As you move from the left to the right, the star is hotter, and as you move from the bottom to the top, the star is brighter, or more luminous. You may notice that the color matches the temperature. Red stars are colder, and blue stars are hotter. All stars fit on the diagram, and properties like size and distance of a star can be derived from their location on the diagram. Back to our protostar. At this stage, the protostar is close to the sun's size, only slightly bigger. Outside the star, a protostellar disk begins to form. This ring of matter will eventually form planets, like our own. The star slowly increases in temperature and dims in brightness. Depending on the star's mass, it will land on different parts of the HR diagram and stay there for the main sequence. Finally, at stage 6, the core of the star is hot enough to initiate nuclear fusion. The star will combine hydrogen in its core to create helium, making a lot of energy in the process. At this point, a star as massive as our sun will be around 1 million kilometers in radius. Now, we reach stage 7, the main sequence. The star is finally stable and now resembles the sun we see in our sky today. This stage will remain stable for around 10 billion years, as it slowly burns its hydrogen into helium. A star will spend around 90% of its lifetime in this stage. But not all stars are the same mass as our sun. Some are bigger, some are smaller, and these differences greatly affect a star's journey throughout its life cycle. If an interstellar cloud fragment has too little mass, it cannot form a star. These failed stars are called brown dwarfs. Brown dwarfs are kind of like when you're trying to start a lawnmower, but you don't pull the cord hard enough. It won't start. Brown dwarfs don't gather enough mass for their gravitational pressure to kickstart nuclear fusion. Brown dwarfs don't do anything. But if a star has barely enough mass to start fusion, the star will become a red dwarf, which is over here on the HR diagram. Red dwarfs have long lifespans, trillions of years, and are very common in the universe. In fact, their lifespan is longer than the age the universe is today. But what happens to a regular main sequence star? Eventually, the star will run out of hydrogen in its core to burn, leaving only helium. Without hydrogen, the star will not be able to continue its hydrogen fusion, and gravity will overpower the minimal nuclear force pushing outward, leading to the now mostly helium core of the star to collapse inwards. Then, the outer layer of the star will expand and cool, still composed of mostly hydrogen. This process moves the star to the red giant branch in the H&R diagram. Because the core is now much more dense and hotter, the star will begin helium fusion. Depending on its size, the star will repeat this process, burning through heavier and heavier elements, primarily carbon and oxygen. Finally, we reach the death of the star. Here's where things get really crazy. Smaller stars, like the Sun, will form red giants, which will continue to burn through elements until they reach iron, where they stop, since iron cannot participate in fusion. They leave behind a white dwarf all the way over here on the HR diagram. These stars do not host fusion in their core and glow only because of residual energy. As this energy runs out, the star will slowly turn into a black dwarf. Red dwarfs are theorized to also become white dwarfs after they turn into blue dwarfs. On the other hand, when larger stars run out of fuel, the process is a little more explosive. When these stars reach iron, they collapse so violently they create a supernova, which blasts heavy elements across the universe. These explosions leave behind nebula, where new stars can form and start the process all over again. They also leave their dense cores as neutron stars, and, due to the conservation of angular momentum, these cores spin very, very fast. Sometimes, a neutron star's magnetic poles won't align with the way it is spinning, creating a bunch of flashes that produce some weird readings called the lighthouse effect. And if the star is truly massive, it'll leave a core so dense it collapses into a black hole. Black holes have gravity so strong that even light cannot escape it, leading to some Einstein-level hijinks. To quickly recap, protostars form from collapsing clouds of dust. If they have too little mass, they turn into inert brown dwarfs. Otherwise, they fuse hydrogen in the main phase. Small main phase stars are red dwarfs, slowly burning for a long time. Medium stars turn into red giants, and eventually white dwarfs when they run out of fuel, cooling off into black dwarfs. Large stars turn into red supergiants, which explode in supernova, either forming neutron stars or black holes. We learned a lot about the stars in space, so let's come back down to Earth for today. It's been a blast.